Hey, what's up, guys? We have got a little bit more to do in section 2.5, in which we're learning to reason using properties from algebra. And most recently, you'll learn to use algebraic properties of equality in order to justify the steps you use to solve an equation. All right, now what I told you was this is us building kind of a road, I suppose, to get you to where you need to be when we're proving statements about figures, writing proofs. And we're getting a little closer to that. This is learning goal 2, again, despite the 1. You'd think I would have changed that by now, but I didn't. Anyway, you're going to use properties of equality involving segment lengths and angle measures in order to justify statements about geometric figures. All right, so we're going to learn some more properties of equality, and they're going to involve segment lengths and angle measures in particular. And let's get to those properties of equality to begin. Now, I want to tell you this right off the bat. These properties of equality that we're going to learn in this video aren't properties that you would actually use to solve an equation like the addition property and subtraction property of equality were. All right? Yet, they are still important, and they're more important to geometry than some of those properties like the division property of equality, which truly never gets used in geometry. Okay, the first of these properties that we're going to learn is called the reflexive property of equality. And this property, very, very simple to use, okay? Very simple to understand. Just got to remember the name. That's the tricky part with all the other properties and postulates and such that you're going to learn. All right, here's what the reflexive property of equality is about, though. For any real number, A is equal to A. Now, this is exactly as simple as it seems. It might be seemingly useless, but it is as simple as it seems. This property simply says that a number is equal to itself. So for instance, 5 equals 5 because of the reflexive property of equality. Negative pi equals negative pi because of the reflexive property of equality. All right, very basic. I promise there's a good use for it in geometry. Now, what's going to happen in this particular set of properties that we're looking at is we're going to look at these properties from 3 different perspectives. We're going to first just look at the real number property version of the reflexive property in this case, and symmetric, and then transitive properties after that. All right, so this, we're using a real number. But what I'm also going to do is I'm going to show you how this property looks when it involves a segment length. Okay, that's the next typed thing that'll be on your screen here in a moment. And then we're also going to look and see what does that property look like if it's dealing with angle measures. So 3 different versions of the same property, but they are the same property. All right, well, with segment lengths, here's how the reflexive property would look. If you have a segment AB, then the distance from A to B is equal to the distance from A to B. All right? And then with angle measures, for any angle A, the measure of angle A is equal to the measure of angle A. All right, now let me give you an idea of where you actually might use the reflexive property. I'm going to draw a couple figures real quick. Now, I've drawn a couple pictures. In this first one, sometimes what we try to do is we try to prove that triangles are congruent to one another. And it often happens where you have triangles, such as triangle ABD and triangle CBD, that are reflections of one another in some line. Now, when you're trying to show that the triangles are congruent, you have to say that they have all their pairs of sides and all their pairs of angles are congruent to one another. And in the situation like this, where a segment is shared by this triangle and this triangle, it's often useful to use the reflexive property to simply say that segment BD is congruent to segment BD, because that distance from B to D is going to be the same in this triangle as it will in this triangle, right? So that segment has to be congruent to itself. That's the reflexive property with segment lengths. And then let's say I was wanting to compare maybe triangle XTW with triangle VRW. And I was wanting to show that all its sides and angles are congruent. Well, one of the angles that happens to be congruent is angle W. Angle W is part of, whoops, I didn't mean to draw there. Oh, definitely didn't mean to do that. Let's undo. Okay. Anyway, triangle RVW and triangle XTW both contain angle W, and so it's useful in trying to show those triangles are congruent to be able to say that angle W is congruent to angle W, which is essentially the same thing as saying that the measure of angle W equals the measure of angle W. That's the reflexive property in practice. Next, property. Now here's another property that you might think won't get a lot of use, and actually it will get much less use than the other two that we're learning. But it's called the symmetric property of equality. The symmetric property of equality says this: for any two real numbers A and B, if A is equal to B, then B is equal to A. Alright, now basically this is telling you that if you want to switch what's on the left side of the equation with what's on the right side of the equation, that's fine. That's all they did. They moved A to the right side of the equation and then B to the left side of the equation, and the two sides were still equal to one another. Now, a place where you might see this, let's say you're trying to solve an equation like, whoops, that's not what I meant to do. Yeah, I'm doing all sorts of stuff right now. Okay, hold on. Let's say we were trying to solve an equation like 7 plus 4x is equal to 5x, and we were trying to justify our answers and so forth. Well, the first thing that you would do, well, that's given to us. First step you would take is you would subtract 4x from both sides, right? So you get 7 is equal to 5x, and you use the subtraction property of equality to get there. And then you would divide both sides by 7, so we get 7. Oh, you know what? That's not equal to 5x, is it? Alright, you get 7 is equal to x when you subtracted 4x from both sides. And then, oftentimes, we don't like leaving the variable on the right side of an answer, and so we switch the two sides of the equation. Instead of 7 equals x, we make it x equals 7. And when you just switch the sides of the equation like that, you're making use of this new property that we're talking about, the symmetrical property of equality. Okay, so that's where the symmetric property of equality is used. Let me show it to you in the forms of segment lengths and angle measures. For any two segments A, B, and C, D, if the distance from A to B equals the distance from C to D, you can switch the two sides of the equation, and you can make that the distance of C to D equals the distance from A to B. Alright, or with angles, if I know that two angles are such that the measure angle A equals measure angle B, then it's also true to say that the measure angle B equals the measure of angle A. Alright, I don't think any more explanation is needed there. Let's go on to the transitive property of equality, which is the one that requires the most explanation of these three. Transitive property is going to involve three numbers at a time. A, B, and C if we're just talking about real numbers. And if I tell you that A is equal to B and B is equal to C, that means then that A has to be equal to C. Alright, now let me describe to you what's going on with this property. There are three numbers here, but these two, A and C, both happen to be equal to the same value, B. And as you might imagine, if two numbers are equal to the same thing, that means they have to be equal to each other as well. So if A equals B and B equals C, since they both equal B, that means A is also equal to C. Right? Okay. Now, here's how that looks with segments. For any three segments, A, B, C, D, and E, F, if A, B equals C, D, and C, D equals E, F, well then A, B, and E, F would both be equal to the same thing, and so they would be equal to one another, right? Or, with angles A, B, and C, if the measure of angle A equals the measure of angle B, and the measure of angle B equals the measure of angle C, then the measures of angles A and C are both equal to the measure of angle B, so they have to be equal to one another. Want to illustrate that with a geometry problem real quick. I'll put up a whiteboard. And this is so you can see where the transitive property would actually be used. Let's suppose that the distance in this triangle from A to B is equal to the distance from B to C. In other words, this segment and this segment are congruent to one another. And let's further suppose that the distance from A to C equals the distance from B to C. Now I'm going to label this differently just so that it's a little more explainable. That would mean that this distance and this distance are the same. Well, if both AB and AC are equal to that same length BC, then what I can conclude with the transitive property, what I conclude with the transitive property then is that AB has to be equal to AC. Alright, so really all three segments are congruent to one another. And then what conclusion can we make about the triangle? Well, based on these two pieces of information right here, and then the use of the transitive property, we're able to conclude that triangle ABC is equilateral. Alright, so you've learned some new properties and you've seen how a few of them apply to geometric shapes. Great. Now let's go on and do this. One of the things that I need you to be able to do is simply to look at some conditional statements. That just means if-then statements. And to understand what property or postulate or theorem you can use to justify the conclusions being made by those statements. Alright, so for instance here, if the measure angle K equals 35 degrees and the measure angle G equals the measure angle K, what property of equality can you use that would justify the fact that the measure angle G is also 35 degrees? So I'm going to let you pause the video here in a moment as soon as I'm done giving directions, and you're going to name the property of equality that justifies that statement. But before I let you go on that, we learned 3 properties of equality in this video. You learned 5 in the previous video. There was the addition, subtraction, multiplication, and division properties of equality, as well as the substitution property of equality, and any of those could be the justification for these 4 statements right here. Alright, now pause the video and then check your answers in a moment. Okay, for this first statement that says that if the measure angle K equals 35 degrees and the measure of angle G equals measure of angle K, that the measure of angle G equals 35 degrees, that statement could actually be justified 2 different ways, and I would accept either one of them. One property you could say that you would use to justify that is the substitution property of equality. So if you put that, I can count that as correct. And the reason the substitution property would work is that you can say you took the measure of angle K in this equation right here, and you replaced it with 35 degrees because that's what the measure of angle K was equal to. So you substitute this value right there. But you could also justify this as being the transitive property of equality, because I'm telling you basically that 35 degrees and the measure of angle G are each equal to the measure of angle K. And if they're equal to the same thing, they've got to be equal to one another as well. Alright, substitution property and transitive property often are very similar to one another. There are instances where you definitely choose one over the other though. I think substitution property is probably the better of the 2 answers here. Both work fine though. Alright, with part B, if FG is equal to ST, if this distance equals this distance, then the FG plus XY equals ST plus XY. No. All that happened from this equation to this one is we added the same thing to both sides of the equation, added XY to both sides. And so that's an example of the use of the addition property of equality. Alright, hopefully you're 2 for 2 here. Then part C. If 1/5 times x minus 2 equals 12, then x minus 2 equals 60. Alright, hopefully you found that that was the multiplication property of equality. And hopefully it's really easy to see, I keep saying hopefully, but I mean it, that if you multiply the left side of this equation times 5, well, 5 times 1/5 is 1, and it just leaves you with x minus 2. and then multiply the right side of the equation by 5, 12 times 5 equals 60. That's how you get from this first equation to the second equation. Multiply both sides by 5. There you go. That's the multiplication property of equality. And then finally, in part D, if the distance from J to K equals the distance from M to N, then M to N is equal to J to K based on the symmetrical property of equality. Good so far? All right, we got one more example to work through here. It's a doozy, I won't lie. Here it is. All right, very similar to something that we worked in class. Now, what I'm wanting you to do is to take this diagram and to use this information here that the measure angle 1 equals measure angle 3. In fact, let's go ahead and mark that on the diagram. The measure angle 1 equals measure angle 3. And I want you to fill in the statements here, the reasons that justify these statements that ultimately show that the measure angle JKN has to be equal to the measure angle MKL because of those two congruent angles. I'd like you to pause, see if you can fill in those reasons, and then come listen to me and why those reasons are what they are. Go ahead. Okay, the first thing I need to do is talk about these statements here and why they're able to get us to the fact that the measure angle JKN equals the measure angle MKL. We're starting here with what's given to us, right? Weren't we told that the measure angle 1 equals the measure angle 3? So just like with your equations where you were writing the reasons for the steps and you started with given every time, you start with given here. Always you start with information that's told to you. That's an assumption you're making for the problem. And then you show why that assumption or assumptions, because it can be more than one thing, leads you to the ultimate conclusion that you're trying to make. All right. And if the measure angle 1 equals the measure angle 3, then it should make sense that if I add the measure angle 2 to both sides, I still have the left side equal to the right side, right? I just took the measure angle 1 and added the measure angle 2. Also added the measure angle 3 with the measure angle 2. If you add the same thing to both sides of the equation, that's the addition property of equality. Now, why do I want to add the measure angle 1 with the measure angle 2 and the measure angle 3 with the measure angle 2? That wasn't random. If you look in the picture, if you put angles 1 and 2 together, they together form angle JKN. And that's one of the angles that I wanted to show was congruent to the other angle, MKL. And angle MKL is made of putting angles 2 and 3 together. All right, so ultimately, this is really angle JKN's measure right here, and this is angle MKL's measure. Now, I have to actually state that formally using the segment addition postulate. Let me write that in. Which is different than the addition property of equality above. Using the segment, what am I thinking? Using the angle addition postulate, you can say that when you put these two angles together, it equals this larger angle, and that when you put angles 3 and angle 2 together, it gives you this larger angle, MKL. All right, and then finally, if I know that angle JKN equals the sum of the measures of angles 1 and 2, and that the measure of angle MKL equals the sum of the measures of angles 3 and 2, and I know that those quantities are equal based on the previous equation right here. I know the measure angle 1 plus the measure angle 2 is in both those equations. Actually, I meant to highlight. And the measure of angle 3 plus the measure of angle 2 is equal to that. Well, that makes these two things equal to one another, doesn't it? And you could justify this a couple different ways. Let's say that we're using the substitution property of equality. All right, because all we did was we replaced the measure angle 1 plus the measure angle 2 with an equivalent value, the measure of angle JKN. That was the left side of the equation. And on the right side of the equation, we replaced the measure angle 3 plus the measure angle 2 with its equivalent value, the measure of angle MKL. All right, that's a very basic example of a proof where we justified a statement about a figure using properties of equality. I'm out. See you next time.